much.
Hello, thank you for coming to this episode on Hubs TV. Today we will be recapping the week 2 of Cosmology from Home, which is an innovative conference with a new format, which is particularly tailored to be done remotely and from any place in the world. And we'll be discussing with the general public, and that would mean you, what we've been talking about over the past week. Before I go on, please let me introduce Ainkaran, who is a PhD student here.
Hi, thank you, Daniela, for the nice intro. Oh, yeah, as Daniela said, I'm a PhD student in theoretical cosmology, so that's what you're going to be learning a lot about. And this conference, which has been great and been run by some of the lovely people here who are joining us tonight. So we'd like to be able to now just introduce Sean and Diana and Nico. So Sean here is one of the, and Nico, two of the co-organizers of Cosmology from Home. There are a few other co-organizers as well, and they've done a brilliant job of getting this international cosmology conference going. And yeah, I'll let them introduce themselves, and then I'll introduce Diana soon, which most of you people already know.
Hi, thank you for the nice introduction, and thank you guys for hosting this today. I'm really happy to be back here on the Cosmology from Home HAPS account. We did 3 really fun broadcasts last week. I'm happy to be back doing another one. So yeah, I'm a postdoctoral researcher over at the ULB in Belgium. I focus on dark matter and basically trying to figure out what we can learn from the universe about dark matter. It's a super fun topic, and I love talking about cosmology, which is why I'm here frequently on HAPS chatting to everybody about cosmology. That's it from me for now.
Yeah, and Sean, would you like to quickly introduce yourself?
Hello, yep, I'm Sean. I live in Auckland. I'm a postdoctoral researcher part-time and part-time trying to share research with the general public through various business ventures. My cosmology work has never been able to settle down in one place, so I've worked on stuff from local underdensities, which we call cosmic voids, through to early universe inflation, and even trying to model the landscape of vacuum energies from string theory in my latest forays.
And Nico, another one of our Cosmology from Home co-organizers.
Hello everyone, hello from Newcastle in the UK. My name is Nico and I am here for the first time, so please be gentle with me. I work in cosmology at Newcastle University, and I also co-organize Cosmology from Home with Sean and some other wonderful and lovely people. My expertise, you can say that it's late time cosmology and detectors, because I have some experience in that from before. So I'm super excited to be here tonight.
Thank you very much.
And last there was me, which of course I forgot to introduce. So I am Daniela Sade, and I am a postdoc at the Institute of Cosmology and Gravitation in Portsmouth, which is in the UK, even though right now I am in Italy, which is what I'll be talking about. And maybe it's a bit cliche, but can we ponder for 5 seconds about the beauty of the fact that we're speaking from 5 different locations? I don't know, I just think it's beautiful. And also, actually, Sean, what time is it where you are?
It's 7 a.m., which is relatively early, but I actually had to get up at 5:45 because I was participating in a part of the conference, a conversation about a project to kind of adapt the way we do peer review a little bit. So I was in that discussion until like 2 minutes before 7, and then I jumped over to join you guys.
Great. So you're in the future.
7 doesn't feel too late today, too early today.
Yeah. So you're in the future speaking from tomorrow. That's great. Okay. So as I briefly mentioned at the start, this is an innovative conference. It's called Cosmology from Home. It happens entirely online and entirely remotely, but it's not going from one Zoom meeting to another Zoom meeting. It was actually tailored in such a way that it would work remotely. And if you look, there have already been other broadcasts about either what happened until then or some Ask Me Anything. There will be other Ask Me Anything. For today, we will be recapping all of the cool things that happened over the past week. So this will be the first recap of week 2. Actually, we will not be recapping again what we already recapped, but we will be recapping that which we did not recap already. So there have been several cool things, and I would like to start with the plenary sessions we had on simulations. Simulations are becoming increasingly important when it comes to using artificial intelligence in cosmology. Sean, can we tell us a little bit about it?
Yeah, so I was involved in watching the session on a group called Camels. I've actually forgotten what Camels stands for, but what they were doing is not just simulating, but also machine learning, which is an even new development in how to extract cosmological information. So simulations essentially means not trying to kind of come up with equations or models that can be used to directly parameterize the stuff we observe, but instead just saying, okay, here's a likely initial condition of the universe. What are the laws of gravity? Evolving that forwards in time and seeing what it looks like at the end. And then that's been going on for decades now already. The new thing that these guys with machine learning is doing is, instead of then taking the final output of the simulation and trying to kind of extract information from it that would then match what we observe, they get a machine learning algorithm. And I have to admit, I don't know machine learning super well, but they get a machine learning algorithm to extract that information for us, which does turn it into a little bit of a black box. You don't understand exactly what pieces of the final result of the simulation are giving you the information about the cosmological parameters you're interested in. But in principle, it can be more powerful, the same way that AlphaGo can beat us at Go, or even beat us at chess nowadays. This machine learning algorithm can kind of beat us at getting constraints on cosmological parameters. There's a few other thoughts I have that might be interesting on that if I can go into, but I appreciate what other people's thoughts are on machine learning and cosmology. It might be that people didn't come to that session, so they could just give a general idea.
So that session was one of the late sessions, by the way. It's one of those sessions that are more easily accessible to those on the eastern side of the globe. So it happened, I think, when it was 1 a.m. in the UK, if I remember correctly. Yeah, so I admittedly, for that reason, I only heard part of it. It was actually really cool. So I went to, I watched the talk and I read the papers afterwards. One of the good things about this approach is that it can really reproduce in a fraction of a second something that normally takes hundreds of CPU hours, right? And in fact, one of the things that I find fascinating about machine learning is that in some particular ways, training a machine for a task is not so different from training a human. Essentially, you present a machine with a large number of examples, and then the machine tries to figure out all the correlations and tries to figure out what it is that, so if you're given example X, what it is that's coming with X, if you're receiving an example Y, what it is that is coming with Y. It tries to build up correlations and it tries to learn what it is that comes with something else. I find this fascinating because by observing my 2.5-year-old nephew and niece, it's not very different the way they're learning. They're just trying to build up lots of correlations to figure out the world. And I would like to, on this subject, I would like to go to Diana, who also went to the theme discussion about numerical tools. So what can you tell us about machine learning and numerical tools and stuff?
Well, about machine learning, I don't really have much to add other than, to me, it still feels like a magic box. Like we pour stuff in and just hope that something good comes out. I've attended lots of machine learning courses by now, and to me, it's still just like this magic black box where people who know what they're doing put stuff in and give me good results. And for now, I'm happy with that. I hope that in the future, I will get better at machine learning myself. But I'm actually much more involved in other types of code that don't rely on machine learning or artificial intelligence. I'm a co-developer of two big cosmology codes, which are Class and MontyPython. There are many codes used by the community. So actually on Friday, as part of the conference, we had a themed discussion on the topic of numerical codes, which ones are available, which ones, where do we think there are gaps? And I thought it was a super interesting discussion to have, people coming from many different perspectives. On the one hand, there was the idea of how can we actually find these codes? If we find them, how do we know which to use? Sometimes you might find 3 or 4 codes that do exactly the same. So we had a strong discussion about, whether we rely on the citations or how well documented the code is. We also extensively discussed Nico's repository that, Nico, if you want to post a link to in the comments, that would be great. Nico has cultivated a repository where we have all of these codes, or most codes, listed, which makes it very, very easy for people to find. But of course, the counterpart, Nico, I'm sure you can address this more, is that it's a lot of work for one person. So, Nico, do you want to discuss your repository of codes?
Absolutely, if people are interested. So it started very strangely on Twitter, actually. People started talking about how there are resources for some code, but there is no one particular place on the internet where you can access it. So, for example, if you're starting in like as a PhD or a master student or undergrad, doesn't matter really the level, sometimes you don't know where to find a code or a library that is open source that you could potentially use for your research or just to play around with. So it started on GitHub, and then some people joined. Like I created it, I remember it was nighttime, and then in the morning it blew up because people started adding the code. So it's not just my work. I want to emphasize that a lot. It has to be a community effort. So I want to thank everyone who is contributing. So basically, the GitHub repository is open. You can submit a pull request, and then we can see what you're adding there. So the code is not just cosmology; it is also actually started as a high energy physics repository, and then we have some astronomy and of course as well cosmology code. So basically, you can browse around. People who are not in science, they can also you're more than welcome to try to use these libraries and see how things are done, because it can be super interesting, especially because some of these libraries have the examples. So if you know a little bit about, for example, Python, then you can just run a notebook and see the code, the whole process. So basically what we discussed during the conference is not just my repository, but how to deal with this. Like, do we keep it on GitHub, for example, or do we take it to website? Who maintains it, because it cannot be one person job. Then we also talked about what I really want to thank Diana. It's the code, the best practices in the code. So the point of writing a code is not just for your own research, right? If you're part of a collaboration, then you are sharing your code with others, or you are contributing. So what is the best practice in that sense? What else is very, very important is how you're documenting, how you're writing, how you're communicating it, and so on. So it was a very, very good discussion and very helpful for everyone involved. So thank you again to Diana and to everyone who contributed. So I'll maybe Daniela, you want to take over now? I don't want to take a lot of time talking.
As in, yeah, I can take over, Nico. So yeah, I was just going to say, one thing that a lot of our audience might find interesting with a lot of these codes is that they actually get implemented in the real world a lot of the time. So the stuff that we're talking about, machine learning, a lot of people have heard about machine learning being used in the industry, and these advancements are very exciting because it provides a much better, more efficient way of corporate processes being done, stuff like this. Various companies, not just those involved in research, industrial research, but even those that are very commercial. Those names kind of escape me, but like Apple, for example, would be investing in something like machine learning, and because there's a very exciting prospect for it. You probably know that a lot of these microchips, which are motivated by these advancements in software, there's a symbiotic relationship, I guess, between the two. And one thing that I should have said before introducing Diana, is that she was one of our plenary speakers, actually talking about the use of the data from the cosmic microwave background as a probe for early universe physics. So Diana can probably, I think you can talk more about. And just to clarify, when we've said plenary speakers in these previous, and there we go, yeah, we've got another cosmic microwave background thrown up there. So this is a picture of cosmic microwave background. This is what we call like the baby picture of the universe. So, and Diana is an expert in this, and that's why we have her as a plenary speaker. I'm very lucky to have her. So yeah, Diana, do you want to give us a bit more about data analysis in numerical tool?
Sorry, I was just going to jump in with a quick comment before Diana talks about the thing you were saying, Angaran, about big companies using algorithms that cosmologists might devise. There's actually, IBM actually employs someone to do numerical relativity cosmology work, Eloisa Bentavenia, and her day job is doing cosmology, but IBM think that's valuable enough to them that she will invent algorithms that they can use to do, I don't know, make their international business machines better. So I just wanted to jump on that because it's short before Deanna goes on a new topic.
Yeah, I think it's wise. CMB was mentioned. You should get any words in while you can. Thank you once again for giving me the perfect excuse to bring up my CMB image. A broadcast cannot go by where that doesn't happen. Thank you for your nice comments, Angaran. I was very happy to be invited as a plenary speaker. And thank you to the organizers, of course, for inviting me. So I want to go back a bit to what we were saying before about the discussion we had on coding. Nico highlighted that one of the things we did discuss was good coding practices. And I do want to say that I contributed a lot to this discussion, but most of it was not, like, I can't take full credit for this because a couple of weeks ago I attended another conference on coding called the Escape Coding School. And it is focused mainly on PhDs and postdocs within our community trying to teach us how to code properly. And I think it's something really important because we have these big collaborative codes where everybody comes in with their own coding style. And at the end of the day, we're not programmers. We're not experts in what we're doing. We will Google how to code a function and throw it in our code and hope for the best and hope nobody needs to reproduce it. But we are trying as a community to be better at coding so that our codes can be more useful to more people. And this is something we also discussed on Friday. And I think that was very important. And I just wanted to mention the Escape Coding School because it was a big influence on a lot of the points I brought up in the discussion. So onto the thing you mentioned, Angaran, about how we actually use these different data sets. So of course we have amazing data from the CMB, from large-scale structure, from pretty much any cosmological observation. By now we have this amazing set of data. We have that on one side, and on the other side we have codes that can predict what the data would look like given a specific cosmological model. So a lot of what my work actually is putting these pieces together. So we feed the data into one code. This code then builds what we call a likelihood, which then tells us how likely a different cosmological model is given the data that we have. So we put all of these pieces together. On the one side, we calculate a specific cosmological model. On the other side, we compare it to data. And we put these codes together in a way where we basically run like 1 billion simulations of the universe. These are relatively quick. And we find which version of the universe that we tried best fits the data. So that's why it's important to have so many big codes. And I often joke that by now my work is like 90% debugging, 10% coding, and there's not much physics involved anymore. But physics now is really done at the coding level, at least in my field. There's of course many people not touching codes, but for me it's very, very coding based now. Sean, I think you wanted to tell us more about machine learning and the Camels project. And that is something that I'm super fascinated to learn more about because I've only watched half of the talk. I still need to watch the rest of that talk.
Yeah, so the thing I wanted to say is, so the way that machine learning is normally used is to say you've got this kind of black box and you just get better constraints on your parameters, that the machine will just look at all the data, you tell it what cosmological parameters you put in to your simulation as your training set. You make lots and lots of simulations telling the machine every time what your cosmological parameters were. And then you run a simulation without telling it the parameters and it tells you what parameters you used. And then the hope is that you can then, if your simulations are matching the universe, the same physics, then you can apply your machine learning algorithm to the observations and it'll say, here are your cosmological parameters. Now, there's a very common criticism of that from the community, which I think is quite a valid one, which is it is a black box. How do you know that the universe is, first of all, matching the simulations correctly. If your simulations aren't right, the machine, garbage in, garbage out. If your simulations aren't right, your machine learning algorithm is also going to give the wrong answer. But also, let's say the machine learning algorithm improves your constraints on certain parameters. You don't know why, you don't know how it did that. And it's not clear what you gain by just having slightly smaller constraints on certain parameters. Maybe they then are in tension with other observables, but you don't know what physics it is that caused that tension to occur. So what I kind of like the idea of is turning all of this on its head. The same way that, going back to like AlphaGo, beating humans at Go and beating humans at chess. Great, okay, you've made a wonderful algorithm that can beat people at chess. That's wonderful. But it's also made people better at chess, because people can analyze the moves of, say, AlphaGo and go, why did it make this particular pawn move in a chess game? And then, okay, you have to sit for hours and hours and analyze and think and get a different type of more less black box type of chess engine to tell you why that was a good move. And then eventually you go, okay, this was the right move. So turning that on its head and doing the same in cosmology, let's say you run your machine learning thing and it makes a certain cosmological parameter twice as well measured. You can then think, why? There's some physical effect in the universe that is useful for constraining this cosmological parameter that we didn't yet know of. And then keep tweaking your algorithm and removing data sets and adding new data sets in, and eventually work out what it was that made that parameter better measured, just like you can work out why this particular move in a chess game was actually better than what the best engines suggested because some machine learning algorithm found it. And I think that is something I'm really excited about in the future for a use of machine learning, is not just for measuring our parameters better, because then it has all of those issues of like, if you don't know why, you don't know whether you can trust it, but actually just helping us find out the ways to constrain parameters better and then learning from that some physics. It requires a lot of tweaking of the models and removing and adding data sets and things to see exactly what's causing this improvement. But that's what I personally am looking forward to from machine learning. Yeah, in the chess algorithm metaphor, working out, it'll make better moves and then we can work out why they were better moves. But it'll tell us where to look. It might not be, the final product.
I just wanted to jump in and make a quick chess comment. So one very famous player, which Sean might be familiar with now because he's been getting very into chess himself, is Vician, and he used these training algorithms so religiously, actually, and sort of one of the things that kept him up as the top player back in his day in chess. So it shows how powerful these algorithms and stuff can be for making somebody into a great chess player. And what was really interesting was that Vichy completely relied on these algorithms. He would just recite and learn them, and he maintained first position in the world for many years. And eventually Magnus Carlsen came in, who was a much more of a, I guess, if you want to say, natural player. He wouldn't rely as much on these algorithms, and he would try to have openings that we call in chess that were more sporadic to kind of throw off these algorithms, because these algorithms naturally, in the same way you kind of think of a bell curve that talks about probabilities, these algorithms are naturally going to go for the most probabilistic move. So the best way to kind of beat them is to be unpredictable. So that was just a quick little side comment on chess.
Great, thanks, Engaran. I actually thank you for this. I actually wanted to jump on something that Sean said, and also Diana. You've talked about big data, and you've talked about the interpretability of big data, the fact that it can be difficult to understand how we came to some answer. I thought that was really interesting because of late, people speak of big data as if they give you answers, and answers that are correct or easy to interpret. Instead, it seems like this answer needs understanding, and its answers may not be correct. So is it possibly true that big data are not necessarily what they are portrayed to be?
I can give an answer there. I'm not sure if it was aimed at me or who that question was aimed at, but I'm happy to jump on that. I think we also might want to make the difference of big data and cosmology and big data in the actual data science world. Because while we deal with big data sets with thousands of entries, I think these pale in comparison to the big data sets of millions of entries per day that people are using. So it's big data for us, but I don't think it's as big data as some people use that term. My partner's a data scientist, so I just felt like I needed to make that clarification. But yeah, I think data doesn't always have the answers. There is always the problem of how you interpret the data, and there is the problem of are you adding your own biases. I mean, if you ask the data a simple question like how many times is this entry in my data set, that's an answer you can get. But then when you try to interpret what this means, then it becomes a bit easier to bias it. And this is why a lot of collaborations actually do blinded analysis, where they don't know exactly what the data is telling them right until the end of the step. So there's different ways you can do this, but one example is imagine you want to see if a specific experiment you're looking at reproduces the results from Planck. Right? If you already want your data to reproduce Planck, you might be more inclined to find this result. Whereas if you completely take off any numbers from your axis, for example, so you just see where your overall data lies, but you don't know the numbers, you just see the shape of the data, then it's a bit harder for you to input your own opinion. So what a lot of big collaborations have been doing is blinding their data so that the people involved don't actually know what the data is telling them right until the final step. And I think this is something that's becoming much more common in our fields, and I think it's something very important. So and thank you for bringing up the CMB again. So your question as to how much can we really trust the data? I think the data we can trust. Obviously, there's always some messy nuisance parameters. Or what was the phrasing today, Nico? We learned a new phrasing for these nuisance parameters. What was it?
I think what you mean, Catherine, what she said, astrophysical noughties.
That's it, the astrophysical noughties. Yes, I love that expression. So you always have these kind of noughties, these nuisance parameters. So there is some clouding of the data, and there is always some subjectivity in its interpretation. But I think a lot of experiments do take steps to avoid that, so that when the data is presented, you should be able to trust it.
Great.
You are muted.
Sorry. Did you want to say add on to that?
I just wanted to add a emphasis on Deanna's point about blinding being important. It's probably important in most fields, but in cosmology, it is just existentially important, I would say, because we don't get the chance to run the universe again. So if you're in another field, let's say particle physics, you're running your Large Hadron Collider and you don't blind your data, you might accidentally do all of these cuts to the data in such a way that you emphasize some bump somewhere and then you claim it's an interesting new bump. Okay, let's say you did the worst case scenario and it gets a large number of sigma and it shouldn't be. You just keep running your experiment, and eventually if you accidentally emphasize the noise, it'll go away because you take more data. But in cosmology, we can't do that. There's one cosmic microwave background, which Deanna's about to flash up. There's one cosmic microwave background. And if we analyze it without blinding our analysis, we don't get a chance to do it again. We now have the countdown happening as well. We don't get a chance to analyze it again. I mean, we can analyze it again, but we don't get a chance to run it again. So if we don't blind, we're like existentially effed up.
Thank you, and that was quite an interesting point. It makes me think also of the concept of experimental bias. So we may think again that that data give you fact and are straightforward to see what it means. But actually, if the experimenter is not careful, it can bring their own biases into it, as Diana was mentioning. And I'm desperately trying to hide the fact that the llama appeared on screen and everybody's laughing about it, but I failed. So I think we should just have this laugh about the llama on the screen that got there, and I should stop pretending it didn't happen. Anyway, going back to data and simulations, it's quite an interesting point. So we have heard about ways to analyze our data, trying to make codes that are more and more precise and more correct about how this happens, and about ways to speed up the way this is produced, and ways about blinding the analysis so that the experimental bias, for instance, don't come in. I think this is quite interesting. I'm basically trying to highlight the complexity that comes into gathering, analyzing, and interpreting the data. I think it's just always worth stressing how difficult it is and how much expert knowledge it requires to interpret them correctly. Nico, you also are an expert in detector physics. Would you like to add some comment about how important it is to carry out a blind analysis for detectors?
Yes, well, from what I know, I had some experience working in xenon experiment before. There's an experiment that is trying to detect dark matter directly. And the experiment, you can look it up. Maybe I can later share a link to what they have. It's located in the biggest underground lab in the world in Italy. So blinding, absolutely. Because if you don't blind your data, you might run into really big problems that you are unconsciously, as everyone said, finding exactly what you want to find. So what they do in detector physics, they you run the experiment, so you take the data every day or for months, but you don't look at the data. What you do, if you look at the old data you collected, you choose one particular part of the data, a really small part, and then you do your analysis there. You, of course, develop your model, so the way you are modeling what is going on there. In the case of this detector is the backgrounds. So it's basically the noise that you want to get rid of, but in order to get rid of it, you need to know what it is and where is it coming from. In a detector of that of this kind is, for example, radon background, so the radiation that's coming from the pieces of the detector, or the cosmic, which is in nuance. So if you would not blind your data, you, as I said, you might find the signal that you're looking for. So as I said, they only look at the small portion of the detector. They decide on what kind of pipeline they're doing for the analysis, for the cuts and modeling, and then apply that to the whole data set, to the whole run, and then unblind, and then see if it works. So far there was no signal found, but it is very, very strict. So no one really looks at the data. What they also do, and I know that they do in gravitational waves as well, is what they call in jargon, they salt the data. So basically they put false positives in order to test. So there is, I think, one person who knows which these, well, basically they put few fake signals. So if your modeling is correct, you would be able to find and exclude those false positives. So it's very, very rigid, and I really admire people who work on analysis in such experiments.
Thank you, Nico. That was very interesting. And blinding is a feature that also came up at this conference when discussing the surveys. And with this, I'm going to go to different parts of the conference. We've discussed about numerics, about simulations, about artificial intelligence. We also had other plenary sessions, and one we had today in particular discussed a large-scale structure. And we had this opportunity to hear about this amazing phrasing of astrophysical motives. Does anybody want to comment on that?
I'm happy to comment here, and I just want to say this talk was absolutely fantastic, and I'm going to mispronounce her name, so let me just check before I mispronounce the name of the speaker, because I'm very bad at pronouncing people's names, and I should have had that open instead of not having it open. Okay, so we had the talk today by Catherine Hymans, and personally I loved the talk. She was so enthusiastic, so motivated. if I wasn't in love with the CMB, I would now be in love with large-scale structure and wanting to work on that, because she presented it in a way that just really captured me. And she had some cool special effects, like putting herself in front of the slides, which made everybody envious. And both speakers today did that. Amazing. So just wanted to say that was an absolutely amazing talk. And by now I've forgotten what you actually asked us to answer. But yeah, I thought that the talk today was a really nice review of large-scale structure, how we use it, what we can do with it, and really what we should be looking forward to in the future. And we talk a lot about gravitational waves being the next big thing, but there's a lot that large-scale structure, which is the overall distribution of matter in the universe, there's a lot that this has to tell us. And within the next decade, we are actually going to get data from upcoming missions. So Catherine discussed, we're going to have the Vera Rubin Observatory, we're going to have the Nancy Grace Telescope, we're going to have Euclid. All of these are scheduled to launch and take first data within the next 5 to 10 years. So it's really expected that we're going to get a boom of data in terms of large-scale structure. So I think that's really, really cool. And I absolutely loved the talk today. I've completely lost track of what you actually asked, but I hope I somewhat answered what you asked.
You did. Thank you. So something that was interesting and that you mentioned, the large-scale structure. I'm going to say a few more words about that. You show the CMB, and I'm going to give you one more opportunity to show it. Enter the CMB, please. Yeah. So
not a llama this time.
The tiny fluctuations we see here are the seeds for everything else that comes. And at this stage, they're also very small, but they go on to form all the structure we see in the universe, the galaxies, the cluster of galaxies, and the way this happens under the influence of gravity has a lot of information about how the universe comes together as we know it. Gravity is really critical in turning these tiny fluctuations that are just 1 part in 10 to the 5 into the gargantuan stuff we see today, stars, galaxies, these big objects, okay? So how can we use them to see whether our theory of gravity is correct or not? What is the best way to do it? And this was one of the themes we had in one of the theme discussion, where we discussed parameterized deviations from our standard model. Engern, do you want to tell us a little bit about that?
Yeah, so parameterized deviations from the standard model sounds like a very technical phrase, but basically what we are saying is that we build frameworks to then come up with ways of working out how far away something is from what we call the standard model. And I'm going to say a few, I'm going to say one Greek sounding letter and a few other letters now called lambda CDM. Now what that stands for is lambda, which is the dark energy in the universe. So that's what we believe drives the accelerated expansion that we see today. And cold dark matter for CDM. So the reason why our model is called lambda cold dark matter is because these are the majority of the components in terms of the energy budget of our universe that we see today. So what we actually see as like what we would normally call baryons is actually the weird part. We're like the unique part of the universe. Everything else is made up of this stuff that we don't really know what it is, dark energy and cold dark matter. And that's I think I'm digressing a bit, but that is what's kind of so fascinating. Like, if you don't think humans are cool, that you should really rethink it, because yeah, we make up about, we're part of the 5% of the universe according to our current theories and measurements. So yeah, now what we talk about in these frameworks to measure these deviations is that we come up with analytical models to see how gravity could be measured to deviate from our current understandings of general relativity, or if we're talking about specifically about the cosmological model, how we could deviate from lambda cold dark matter, or lambda CDM. I'm going to say lambda CDM from now on. So these frameworks are very powerful because they give us a completely model-independent way of testing these theories. Normally, as like a theorist, for example, myself, like it would be tempting just to kind of come up with some model that I think might be physically motivated. What I mean by that is like it follows the fundamental laws of physics and stuff. But then just say, oh, let me just try this model and see how well it matches to the data. But if you actually come up with parameterized parameterized frameworks, then you can actually come up with ways of testing loads of models, and hence a model-independent way of testing these. And we know just from like our various understandings of physics that our understanding of the universe is not just general relativity and dark matter and cold dark matter and dark energy. Like there are other components that we need to understand, because as you probably know, quantum gravity shows like the search for a theory of quantum gravity shows us a bit further. I'll talk a bit more about that regarding one of the other excellent plenary speakers that we've had a bit later on, and why we know that gravity is not general relativity. But yeah, I think somebody else can maybe take over.
Thank you, Inger. So that was a great discussion indeed, by the way. Also numerous, I should say. There were many people. One thing that struck me from that conversation is that how useful it is to look at the problem from different perspectives. So people who were working in this model-independent way of doing it still wanted the people who are doing the model-dependent analysis to go on. And the reason is that the model-independent searches are more powerful at trying to fish for a deviation from something we know, whereas the model-dependent ways are better at constraining that particular model. I thought it was interesting that in the end, we concluded in that discussion that it's still useful to go in all the possible ways, even though this is one of the most powerful to fish for these deviations from general relativity that just keeps being confirmed at higher, it just keeps passing every test, even though we know it can't be the correct answer for all the scales. Isn't that annoying? We know at some point it has to fail, and yet it keeps passing every test. Okay, and on the subject of general relativity and what the real theory of gravity is supposed to be, trademark on real. Inger, and I think you attended another plenary session today by a relatively junior researcher, by the way, great for junior researchers being plenary speaker. And it was about so-called positivity bounds. What are those? It's quite a technical topic, but what is that?
Yeah, so we had a brilliant speaker, Scott Melville. He's actually one of the Cambridge physicists. So yeah, hopefully during my PhD, I'm gonna get a chance to come up with some cool ideas with him. But Scott talked about, as Daniela said, positivity bounds. So what positivity bounds are is that they are talking about how you can use things that we know from it's like the UV complete theory. So what that means is a UV complete theory is what we call something that is going to be our theory in high energy physics, extremely high energy physics as well. We're not talking about colliders. We're talking about things that are starting to probe quantum gravity. So when you want to unify all four fundamental forces, you go to some like unimaginably high energies. And what positivity bounds do is they try to relate low energy physics to these extremely high energy physics. And they use these fundamental principles that we anticipate will still probably be there in these like quantum gravity theories, such as one physical property is called unitarity. And this has come up in other sessions, but just to sum it up briefly, unitarity in a nutshell, is basically saying that all your quantum probabilities have to add up to 1. As we all know, quantum mechanics governs these very small scales and very, and we expect it to be the theory that's going to be, there's going to be quantum natures to things in a quantum theory of gravity. And the other property that we talk about is locality. So locality is essentially saying that basically things are only really going to impact things that are close by. That your forces are going to be local. They're not going to like necessarily like you're not going to be able to cause a massive effect in one area to another. I really fudged that, but and the other more interesting thing, which involves the idea of light cones, the speed of light, is causality. So causality is a principle that comes from relativity, I guess. So causality, as many people know, relativity says to us that nothing can travel faster than the speed of light, and what that means is that you can't have information, for example, being like passed on faster than the speed of light, and this then creates like a sort of barrier that we call a light cone in physics, and nothing can propagate outside of this light cone, and causality is governed by that. I'll talk about what's interesting from Scott's work that we learn about causality. And one other kind of interesting thing, which is a bit more technical, is called Lorenzen Variants. And Lorenzen Variants is basically just us talking about how there's these symmetries on flat space-time. So flat space-time is basically the most boring space-time you can think of. No curvature. You don't have any weird astrophysical objects like black holes or anything, and you just got completely flat space-time. So it's kind of actually hard to visualize because our universe doesn't really allow for that, really. But flat space-time has the symmetry saying that when you move from one point in the space-time to another with a constant velocity, you should have the physics staying the same, and that's what we call Lorenzen variants. So moving from one frame to another with the same velocity, no accelerating velocity, because otherwise you change the space-time. Should give you the same physics. And yeah, positivity bounds allows us to come up with these really cool constraints about theories that are, for example, theories that are different from general relativity, by saying that we know that we've got to have these kind of properties in our quantum gravity theory, so we can then come up with parameters which then can be then measured in the low energies that we measure today. I hope I didn't talk for too long.
Thank you, Engaran. That was really good. And I think other people went to that talk. Diana, I think you were interested in the way the presentation was carried out, aren't you?
Yeah, so again, as I said with Catherine, I think this session today was excellent. Scott Melville did a really, really nice talk. So I've never worked on the topic of positivity bounds in cosmology, and the title of the talk honestly seemed a bit scary. And I watched it today, and for the first time, I really felt like I understood this topic. And more than just understanding it, I understood why I should care about this topic. And I think it's really difficult sometimes for speakers to convince people outside of their field to care for their own topic. So I just really want to shout out Scott here, because I think he did an amazing job. I loved his presentation. He was also walking in front of his slides with a cool green screen trick on Zoom. And I just thought it was a really, really excellent speaker, excellent presentation. And in general, I found that most talks I've heard so far at this conference, especially the plenaries, have actually had a very, very high level. So again, I want to thank the organizers for the awesome plenary speakers we've had, and for allowing early career researchers to actually take these plenary spots instead of offering it always to the same established professor. So just wanted to make that comment, because I really did enjoy both plenary talks today.
I agree, Diana. That was a great thing. Nico, I think you also went to that talk, didn't you?
Yes, I was hosting the session, so it was really easy for me at first. Like, okay, I can watch Catherine's video because it is my field. But then I would like to follow up on what Diana said. Like, it is what Scott is working on is really not my field, and there is always this reluctancy, right? Or will I understand it, because it is completely fully theoretical, and this is not what I work on. So, but he did such an amazing job, and the way he's presenting, it just flows so nicely, and you just want to like tell me more. So I ended up loving it. What I understood is I really am not a theoretical physicist, but basically what they are trying to do, so Scott and his collaborators, is to try to use the framework particle physics does, so on the smaller scales. And this is basically, well, maybe correct me if I'm wrong, is quantum field theory or effective field theory. That's how it's called. And then make some sort of theory that is very general, fundamental. And then, because it can be so fundamental and general, they have to do some criteria. So they say this has to hold, this has to hold, and this has to hold, for example, for causality, because time goes in one direction, right? So this is what Angaran was talking about. And then when you put this criteria, then you bound your theory in a way. I think this is why it's called the positivity bounds. And then they come up with some sort of parameters that have physical meaning, and then they test their theory by basically saying it in a very simple way, constructing the same plots, using this theory, constructing the same plots that we already have from experimental physics. And why they're using this approach, I think, because even though you go, if you can use the smallest scales, so quantum physics, to explain the larger scales, like the CMB, now we need to put the CMB picture again, maybe for Diana, because what you see, the fluctuations in the CMB are quantum in origin. Is that correct? So you are basically allowed to do that. So this is how I understand it. Maybe I did not understand the talk completely as a proper theorist, but I think it was absolutely amazing.
Yeah, no, we can use the data, so the CMB data to constrain these theories. So what Scott also alluded to in his talk was the idea of theoretical priors and how these could be used to actually improve data analysis, which we were talking about earlier. So when we do data analysis, normally we have some sort of what we call a prior. It's basically us going, it's probably something like this, to make the analysis easier for our computers. So they've got, like, if you're looking for somebody, you're not going to look all over the earth, right? You're gonna have some probably vague idea. If you're looking for your kid who's like probably hidden in the closet like multiple times before, you're going to look in the closet. So that's probably a best bet. You're not going to go, like, I don't know, go over from the UK all the way to Australia or New Zealand. And that's what these priors do. And Scott was saying that that these theoretical priors can help us actually improve our data analysis processes. And the other like interesting thing that Nico kind of alluded to. So yes, yeah, the early universe is definitely governed by some quantum theory of gravity, because that's why cosmology is so exciting. So as Sean said, cosmology, yes, it's difficult in the sense that we can't really run anything, but it also gives us the best opportunity to actually get some sort of data on a quantum theory of gravity, because of the fact that the most powerful collider was run in the early universe. That we're never going to be able to get anything like that on Earth. The great part about Scott's talk is that his results already show us that his and other people's results as well. I shouldn't take away the fact that this is obviously a collaborative environment, but yeah, his papers already show us that there are deviations from general relativity, because general relativity says that gravitational waves should propagate at the speed of light. And that's basically what we measured from astrophysical objects, I should mention, not from, we haven't measured gravitational waves from the early universe, which would be governed, as I said, by quantum theory of gravity. And what Scott's work showed is that from these positivity bounds, we see that the gravitational waves from this quantum theory of gravity will be propagating faster than the speed of light, which is weird, because this kind of goes against everything that you're taught as a student in university. You're just like, no, that can't happen. But this is where the idea of causality is given a completely new meaning, because Scott so kindly explained to is that when we normally think about gravity and relativity and stuff, we think about light being the thing that sets our speed limit. Basically, everybody says you can't travel the speed faster than the speed of light. But what Scott's results show is that actually the more dominant thing that comes along is gravity, and that's what governs a new speed limit. And it's so fascinating that we're able to already have this prediction of quantum theory of gravity, and we know that we've got something else coming along to explain this better.
Thank you, Ingran. That was great. And thank you for mentioning gravitational waves. In fact, something interesting that came up at this conference is that it's not just the speed of light underlying the concept of causality, but also the speed of gravitational waves. And we should say really the speed of all the signals. The idea, in fact, is that you can't communicate with the future at a faster speed than the speed of the signals you use to communicate. And this is how the causality come in, and this is how the gravitational waves connect to that as well. Right, so this was, I think this concludes the plenary talks that that happened in the past few days, but we also had theme discussions that were just as interesting. One of the most interesting, I think, was a special session dedicated to equity, diversity, and inclusion. And this is because it's been more and more of a realization of the scientific community that in order to do the best science, you need to be able to access all the best people. Currently, we have people from specific backgrounds only. We are at the same time very diverse and not diverse at all. We're diverse in terms of nationalities. Sometimes we have people from countries that are at war with each other working together. We are diverse in terms of languages. But actually, most of us are still white and most of us are still male. And this is not how the best science is done. We can only have the best science if all the people who are really into science and really into putting themselves into it have the opportunity to do this. So what we discussed was, how can we make this happen? What are the useful things that we already do that can make this happen? And we share the experience that's happening between different institutions. So who wants to go into this? Thanks, Diana.
Yeah, I thought this was a very important, very timely session. One thing I do want to say that I really liked is that instead of starting with, this is why we should care about EDI, this is why I want you all to come to this session, we just started straight with, we assume that everybody here knows that this is an important topic. Here are some initiatives that have been taken. And I thought this was very refreshing because I have attended many EDI seminars, I think we all have. Was kind of dreading sitting in another one of just, here's what we should be doing. Yes, thank you. So I really like that the organizers instead proposed to give it the focus of what has been done, what has worked. One thing that stood out to me, we talked about a lot of different initiatives that people have taken, a lot of different steps that people have been taken, everything from running demographic surveys, voluntary demographic surveys within communities to figure out where problems lie and identify how we can deal with these, to book clubs. There was a common theme that most people said in the wake of George Floyd's murder, in the wake of the Black Lives Matter movement, and a lot of people pointed to this moment as changing perceptions in the field. And I think it was important to notice how many people have kind of had a wake-up call in the community. Of course, there are many people who still need to have this wake-up call. We know that, especially some, perhaps of the older white male generation, still need to come about to these new ideas. But I personally really got the impression that this is something that the community is now behind, that we're actually now pushing for change, and it's no longer just saying we should do something, but now as a community we are pushing for change within the community. And I think that was really nice to see. I think in general, some of the ideas proposed were very good, how they've been implemented, how they're working. Of course, there's a lot to do, but we are taking steps. One thing that I do want to highlight is something that you, Daniela, talked about, is creating these spaces, these safe spaces where people feel comfortable. For an example, you mentioned the woman's lunch, which I'm sure you'd be happy to tell us more about, where it's just creating this safe space where people feel like they can talk freely and have these conversations. And I think that was really, really important. But there was one discussion that came up. It was a question came up based on a question that one of the participants asked of, can we actually really do anything meaningful because all of us have already been ingrained by society? So what really is the point of trying to change it at the academic level when it needs to change at a society level? And there was a very nice message that I heard there of, you might not change all of society, but you can change one person's mind, and that might be enough for them to then change their kid's mind and influence the next generation. And if you can change one person's mind who then changes another person's mind, this is how you gradually get to change. Just one other comment that wasn't discussed so much in the session, but I think we are doing a bit more about now, is holding people accountable for their actions. And this is something that we're seeing more of in the community, and something that a lot of us are getting behind, that people should not be allowed to get away with their bad behavior anymore.
Thank you, Diana. That was really good. And we also talked about widening the participation also in terms of countries and also countries of all incomes. And I think, Ingran, here there's quite a lot that you can say about, also because you and other people are running this UniArc initiative.
Yeah, so thank you so much, Daniela. Yeah, so UniArc is an initiative that I started with a few other students. It's an organization which helps students from persecuted backgrounds and underrepresented backgrounds and other kinds of disadvantages, such as financial, get into universities in the UK, Europe, and USA, and they get these services completely for free. And we started this recently, and we've gotten quite a lot of help from other volunteers who have been willing to volunteer their time as mentors. And yeah, we've gotten some interest in terms of donations. So obviously something like this requires certain donations, and in order to make it run. Yeah, one thing that we specifically want to help these students with is that a lot of these students, as international students, face very specific, very difficult and like huge financial barriers. As international students, you're charged a lot more than domestic students for your tuition fees in the UK, for example. So yeah, and this brings me on to a point that there is one talented student, Aravind Shekhar, who I've just shared the link for, who's actually got a PhD position at Southampton University to study quantum gravity, and he is currently trying to fundraise. You can read more about it in the link. But yeah, no, thank you so much for mentioning this EDI talk. So one thing that came up is the fact that a lot of these collaborations that we mentioned. So, for example, why the collaboration clicked in my head? Not Desi. What is Desi? Okay. Basically, a lot of sorry.
So there was SDSS, sorry? There was Daisy. Yeah, SDSS and Daisy.
Yeah. Oh yes, yeah. So yeah, yeah. So DESI is the dark energy survey, something. But basically, it is a collaboration using telescopes to measure the dark energy in our universe, and these collaborations already have these, or most of these collaborations already have these kind of EDI discussions, which is really like uplifting for people like myself who come from these underrepresented backgrounds. And yeah, there were other various points that have been like raised, which are just so important to kind of like talk about when it comes to making sure that we don't put up these barriers for children who or everybody should know that when it comes to physics, you aren't born to be a physicist. And I'm quoting Daniel Green, a great professor in University of California, San Diego. It just comes with practice. So no matter what your skin color is, no matter whether you're a boy, girl, or whatever, regardless of what your orientation is in terms of your religion or sexuality, etc., like none of those things matter. Physics just comes with practice, and I truly believe that. And one thing that I always come back to as a cosmologist is that in cosmology, we know that we aren't what we call fundamental observers. It doesn't matter where you are in space and time. Well, in space and time, like wherever you are in space, the cosmological principle, which says to us that the universe looks the same wherever you are, which we call homogeneity, and whichever direction you're looking in, which we call isotropy, the universe looks the same. So that tells me that I've got, and everybody else here, that we've all got as good a chance as anybody else to learn about this like amazing universe that we have. So please, if there's one thing that you want to take away regarding these discussions, it's that you've got as good a chance as anybody, even Stephen Hawking, to make contributions to this amazing field.
Thank you, Ingaran. That's very powerful. And I will say it again, if you are someone who is listening, you're a high school student, and you're concerned about whether someone looking like you or of your religion or your background is good for science, you are, by definition. The question is more about whether you like it, whether you're willing to put in the hard work that's into it, but it's not your background. Whatever your color, whatever your religion, wherever you're from, you're good. You're good as you are. And in fact, the fact that not all the people who want to do science can come and do science, this is really the problem, not your background, whichever it is. I should say about that session that we had some great initiatives being carried out by the Sloan Digital Sky Survey, which is a survey that has mapped the structure of the universe to impressive precision. And I've put a link because you can see all the various initiatives that have been carried out, which are quite many. And in some sense, some of them are about things you may think are obvious, but really are not. In a meeting, in a collaboration, how can we make sure that all people can talk? This is really not a trivial subject because it's been shown that depending on how you ask the question, some people may feel excluded. An issue that came up because of this is that of impostor syndrome. So for instance, if you phrase a question in such a way that you ask for excellent people to reply, some people with impostor syndrome, and I'm going to say what it is in a moment, may feel like they can't reply. So impostor syndrome is the feeling of typically high-achieving individuals that they are really a fraud, that they don't deserve to be where they are, and that they're only there because they managed to trick everyone else into thinking they're really, really smart. But this was basically due to a succession of very fortunate events that they didn't really deserve. There is suspicion that it is actually more common among underrepresented groups. And one of the reasons could be that I can see less of people that look like themselves, which may reinforce these beliefs that this is not really where they belong. So because of this, there is time evidence to show that depending on the way you ask the question and depending on the way you organize a meeting, you may increase or decrease participation by your groups. I think other people attending that beautiful EDI session, among which there is Nico, who, well, by the way, is one of our great organizers, and she made this discussion possible in the first place together with the other organizers. The two organizers of that session aren't here, but we've got the two organizers from the conference, and so I will take this opportunity to thank all of them again. Let's say by thanking those who are at this session, and let's say by transitive property, also thanking those who aren't but organize the rest of the conference. Anyway, Nico, can you please comment on give us your comments on the EDI session?
Yeah, thank you. First of all, I think it's super. I'm going to get emotional now. I should not. I should be more professional. But it is really, I think Sean can also say the same thing. It is super important and super rewarding when the goal of your conference was to be super inclusive and to give a platform to early stage researchers, to people from all over the world, are truly global. And we manage that, and then when you say something like that publicly, or when we receive emails or messages, that is the reward in itself. Speaking of the EDI event, I somehow it can be a very tricky issue, and somebody mentioned in the comments, like, we hope that this is going to be a real thing, not just a pendulum, right? So it definitely is not, and there a lot of thought was put into it. How are we going to do it? What I would say that in order for it to happen, it should happen on many levels. So not just on the university levels, and that you have some laws or rules that you need to follow as a member of the university or school. It is also on a societal level, that as a community you need to mention the guidelines. You need to address these issues so everyone is aware of it. And if somebody makes a mistake, and everyone makes mistakes, that you are kindly reminded that maybe you should not be doing that, or something is unacceptable. The third thing, what was already mentioned by Angaran and Daniela, is on a collaboration level. So because collaboration, scientific collaboration I'm talking about, is a different animal, right? So it's not really connected to the universities, it's an international body. And then you have the spoke people, and each of the collaborations now, the modern collaborations, have the EDI committee. Absolutely they have, and they take their job very seriously. From what I know, what happens in collaborations that I was part of before, and especially now I'm part of the LSST desk collaboration, and they take it absolutely super seriously. So we constantly have meetings, and they make sure that everyone is welcome. They want to know that the people who are running the committee are aware of the problems, that the junior people or the new incomers in the collaboration are taken care of. So they have a lot of tricks up their sleeve, and I feel very confident being a part of that collaboration as somebody who started it a few months ago, basically. So I think maybe there are other ways of making it happen, and raising the awareness, and being more inclusive in every sense of the word. But I think those three come to mind. So universities as a community and as collaborations. Maybe somebody else has any idea or any comment on that. But I think it was really great to provide people the platform to talk about and share their experiences, exactly that, what really works and what you would advise from one collaboration, for example, to another, or from one university group to another. So maybe, I don't know, Sean or Diana can say something.
I don't think I can say anything specific. Unfortunately, I couldn't attend the EDI panel because it was at 2 a.m. But was, as an organizer of the conference, totally supportive of its existence. And as I typed in the private chat to the other panelists today, we spent, and Nico knows this as well, we spent weeks and weeks and weeks and weeks and weeks brainstorming exactly how to run that, and not have one of two bad things happen. One, it just be just like everything else, and nothing meaningful came out of it. And the other thing, not having it derail into an argument, which would have been the worst of the worst case scenarios. I mean, I guess the only thing I would add is just a general sentiment that I think in the past, people have maybe argued that a very competitive atmosphere is the best way to get science done, and, the best of the best rise to the top, which I think, I mean, it sounds like a compelling argument when you don't think about it much, but I think it just misunderstands human psychology, and that, first of all, people work better when they're in a welcoming, warm atmosphere, like not in a competitive one. I mean, maybe in elite sports, it's competitive, but then you still want your teammates to care for you and things like that. And then So we tried to make the conference as warm and welcoming as possible so that the best conversations come out. If people are arguing with each other in a kind of adversarial sense, then we just get all defensive and not open about our things. People are less likely to change their minds and say what they truly think. And then, yeah, as Daniela was saying earlier, that it means, or maybe Angaran was saying, if someone is from a background where they don't immediately see themselves as fitting in, then having a competitive atmosphere just shuts them out entirely. Whereas if you see lots of people like you, a competitive atmosphere might, I mean, it's going to shut you out a little bit, but it won't shut you out entirely. But having a warm, welcoming atmosphere helps people to, even if they feel that they don't fit in, still feel welcome a little bit. So those are as the token white person today, token white male, sorry, those are my thoughts.
Thank you, Sean. And actually, I would just like to take the opportunity to remind that Marie Curie herself at some point wasn't allowed to teach physics because she was a woman. That would have been a scandal. So even the great Marie Curie, who won 2 Nobel Prizes in her career, yeah, at some point she couldn't teach physics. I think some other person who happened to be male, though not as great as Marie Curie, was given the opportunity. This is a great example of why it's important to let everyone have a chance of physics. Even though I'm not sure this is very likely, but again, in the off chance that we've got school students listening, we particularly need people who are Black, people from African countries. We particularly need people from low-income countries. The difficult bit here is that, unfortunately, there is no equal opportunity in terms of scholarships. Most scholarships are in rich countries. So this is something that we will probably need to change. We don't yet have equality in that respect. But you know, for what we can do, at least as scientists, we don't necessarily have the levers of the power here. If you are from any of this background, you're most welcome to apply. We would love to see you here, and I hope that things will conspire to have you here. We really need you. We need your point of view. We need your culture, your way of doing things. We need to not be all just equal. Okay, so thank you very much. So we are going to, yeah.
Yeah, Daniela, I just wanted to sort of also use this opportunity to highlight Jocelyn Bell Bernal. So she suffered from a not so welcoming environment in the physics department at Cambridge when she did her PhD, and it drove her to work extremely hard, as she said, so that when they kicked her out, as she expected them to do, she could at least pat herself on the back and say that she did everything she could. But thankfully, that didn't happen, and she came up with some amazing physics. She was the first person to discover pulsars. And oh, can you not hear me?
We can.
I can hear you. I think it's just Nico.
Oh, okay. Okay. Oh, okay, sure. Just checking. Okay, yeah, and yeah, she then starts to fund at the Institute of Physics. So if there's anybody who's thinking of applying for a PhD from one of these underrepresented backgrounds, they have a fairly extensive list on their website. There's the Bell Bernal Fund, which I myself am personally funded by. So I just want to take this opportunity to thank the Institute of Physics and Jocelyn herself for funding me to continue down this academic route, where I hope I can start to invoke a bit of change myself. So yeah, thank you.
I think something that is nice about tonight is that whether or not it was planned, we are showing our human side. I mean, you know, for some reason, it's quite typical of media portraying the scientists as these cold beings who don't have feelings. Well, you have your example tonight. Now we're going towards the end. So because we only have a few minutes left, I would like to ask from each of you to mention one thing that makes you work at your best, if you can pick just one. So for me, it's being happy and feeling accepted by my group, and I've been lucky enough to be in in good groups so far. Nico, if your audio is okay, can you say one other thing that makes you work at your best?
Well, I would have to say the same thing if the environment is welcoming and supportive and understanding. Absolutely the best. You can work on the best topic. If your environment is toxic, it's not going to work. Absolutely not going to work.
Thank you, Nico. I realize it's a difficult question. Sean, what makes you work at your best?
I'm going to come out of left field and say getting a good night's sleep, eating well, and exercising well.
That's a great point, actually. Diana, what makes you work at your best?
I thought I was going to be last. I was still thinking of my answer. I'm going to go slightly with what Sean said and emphasize the taking care of my mental health. This is something that people on HAPS know that I've spoken openly about before, that during my PhD I had a burnout. And I know how easy it is in academia to lose track of your mental health. And some people push others towards this stage. And I think caring for your own mental health and having a support network around you that help care for your mental health are extremely vital. Having people who help pull you back when you're doing too much and perhaps not realizing it. So just in general, taking care of your own mental health and taking care of other people's mental health.
Thank you, Diana. And this is a great comment indeed, especially given that by some estimates, it may be that up to 1/3 of PhD students satisfy the criteria for depression due to various reasons, including financial insecurity and pressures. If you're a PhD student listening, it's okay not to be okay sometimes, and there is help. So if you feel that your mental health is suffering, you're not alone. There are many people like you, and you know what's good? There is help. This is something that can be improved. So also you don't have to accept this as a given. We have a lot of pressures as a society to hide this. I should say that men have even more pressures on this. It's thought of as being unmanly to have mental health problem. No, anybody can have a mental health problem. This is actually something really common. So if anybody who is listening is struggling with mental health problem, you're not alone. There's many people like you. Fortunately, this is something you can do something about. And also there's nothing wrong with you. It's okay not to be okay sometimes. Engaran, after this, I'm sorry to put you in the spotlight after this. What makes you work at your best?
Yeah, those are all excellent points. I've got to say, yeah, being well fed and sleeping well, they naturally, obviously, like there's a symbiotic relationship between, yeah, your mental health and your physical health. And yeah, I've got to shout out my girlfriend, who's definitely made sure that I do stay well fed, because I am just one of the classic physicists who gets obsessed with something and just can't stop looking at an equation or anything. But yeah, I've got to. She's also a doctor. She's not just somebody who looks after. Well, she looks after me, I guess, because she's also a great doctor. But one thing I should say is being true to yourself, I think, is one thing that like makes me work my best. When I try to emulate somebody else, and this has come up quite a lot, is like this comparison between people, and that can really affect a lot of academics' mental health. When I am true to myself, that's when I feel like I get the most productive research done. I know things that other people don't, and then I don't know things that some people do. And that's what we've been talking about today. It's teamwork. It's not as much as the media likes to always focus on one star person, whether it's Hawking or Penrose or I don't know, some other people who've been in the media. There's always loads of people behind them lifting them up. Right, and it's a team effort, and all brilliant scientists will tell you that they will acknowledge the work of others. So don't ever feel like you have to do everything yourself. The reason why we reference papers in our own papers, why we have seminars bringing in these experts, why we have these conferences, is we can talk to each other. That's what allows us to progress. We get all the best expertise all together in one person, and we all learn together. And we don't all know the answers, otherwise physics wouldn't exist. So that's what I think you should acknowledge. Be true to yourself and know what you're good at, and know where you need help.
Thank you, Inger. And it was a very good point that you make. Nobody did anything on their own, and no good piece of science was done by someone on their own. I think you're right. I'll also take this opportunity to thank all the people anywhere that support some scientists somewhere, and also who support some non-scientists somewhere. So we're going towards the end of this, and I would like to mention there were some questions in the comments. Thank you for asking them, and I'm sorry that we couldn't get to them. But we will have an Ask Me Anything on Thursday at the same time as today, and this is where we are going to have a session that is going to be entirely devoted to answering questions about cosmology, data science, whatever. Sorry for not getting to all of your questions today. Fortunately, there will be an opportunity for doing this. Having said that, thank you very much for listening. All hail the llama. There's going to be more llamas and more CMBs, hopefully. Thank you for joining. I hope you like this, and thank you to all of the panelists tonight. And goodbye.